Okay, we're good to go. The stage is yours, Kiran.
Right. So sorry for the technical glitch. Something went off with my Zoom and I had to figure out the last minute. So good afternoon and warm welcome to everyone who made it to our first session today. We are KTH Society, and we would like to welcome you all for our first knowledge sharing session on data-driven motion generation. And my name is Kiran. I'm a PhD at Embodied Social Agents Lab at KTH, working on machine learning for motion synthesis for social group interactions. And I'm also part of KTH AI Society in the team education. So today's session is more or less a basic review of machine learning methods involved in motion synthesis. And the presentation is inspired from few research articles which are cited throughout the presentation. And so the goal of the session is to like lay the groundwork for essential terminologies and also in the topic of machine learning based synthesis, and also introduce some state-of-the-art methods just like Gustav did that demonstrates interesting results in motion synthesis. We will follow up on this with another session where we will discuss some recently developed methods in detail, which include semi-supervised learning, graph neural nets, and probabilistic approaches. And we are also recording this session, so it will be uploaded on our YouTube account later. So if some topic ignites your interest, especially the master students at KTH, and would like to work on some interesting master thesis with us, which has an intersection with computer graphics, social interactions, and machine learning, I encourage you to reach out to us on the contact details shared during the end of this presentation. So, and last thing, before we start, since this is our first knowledge sharing session from KTHEIS, we would appreciate we would take this opportunity to like ask you for your feedback in terms of the style of our presentation, any specific topic you would like to cover later on. So we would love to work on your feedback. So without a further ado, let's begin our today's session. So I'm going to cover a few basic definitions of what motion synthesis is, the architecture of statistical methods, and what kind of training data is available for us. And then we will also look at how can we break down the complexity of these movements and the temporal factor. And in the end, we will be looking at some generation algorithms and control techniques from different machine learning family. So before we start, I would like to get your attention to this interesting video. Right. So now that I have your attention, especially because I believe we must have seen at least one of the movies that the video showed us, which included some interesting animations. So before we get into the technical details, I would like to highlight some known faces from this field. In the bottom right, you can see this is a Japanese telenoid without any limbs. Also on the top right, you can see this San Diego. So UCSD's Diego San. This is another humanoid. On the bottom left, you see an android replica from Ishiguro. They call it Geminoid. And on the left, we have Hanson Robotics, Sophia. Apparently, she also has Saudi Arabian citizenship. So these are some virtual robots from this domain. And so before I get into the details, I would like to highlight why did I show these uh, robots to you is to present this concept called uncanny valley. This is presented. This was so Professor Masahiro from Tokyo Institute of Technology uh, presented this idea that the moment, especially in the beginning, we kind of have this affinity towards these virtual avatars or physical agents, and then suddenly we tend to lose the sense of realism, and that's when we also kind of stop, you know, liking it. And this is especially the uncanny valley of perception. And so the idea is to basically come up with more and more realistic either physical versions or animations to be able to replicate motion, to be able to come up with motion synthesis patterns which are as real as possible. So the way so this is a typical example of how you would perform these experiments. So this is a repetition of a walking sequence recorded by a mocap system. Mocap here refers to motion capture system. This study was done in University of Copenhagen, and these repetitions. So the two actors are basically wearing. The actor is wearing a motion capture suit with markers on it, and I will explain all these concepts later on. And once we are able to simulate, record this data, we can simulate it in any animation engine. So why are we even doing all of this? So the idea is that recently there is an increase in demand of dynamic video games or cinematic or virtual reality content, and that has caused the need to come up with automatic content generation techniques. It's also because the traditional methods are very costly and time consuming. So and the way it is done so far is we have like three broad group of approaches. One is the conventional physics based, where the motion is physically valid and also proportionate to dimensions, or it also reacts to the environmental forces like gravity or friction and so on. The second approach is data driven, the one that we will be focusing on today. And obviously, we can combine both of these approaches to come up with a hybrid approach that has physics and data-driven approaches. Um, a typical architecture it would generally look like this, where we are able to synthesize new movements from this generation model once we learn the movement model from the training data. There's recorded movement segments from an experiment done at motion capture lab. And once the model has fit well with the training data, we would specify some movement specification or a conditioner. Sometimes we also club that with the training data, and then then we post process the output of the model to get an output animation. So what kind of scenarios are we particularly interested in while conducting these experiments? So could be so there have been past research basically on some dance movements, be it Bollywood or hip hop, salsa, And I think for the last couple of weeks, we have been recording sports movement patterns at KTH that included kickboxing, tennis, and so on. And there are like other interesting scenarios where researchers have worked on, for example, waving a hand while walking, standing, and performing other tasks, or fairly shorter interactions like handshake, smoking, eating, and so on. And more recently and even more complex is the group interactions, particularly which I'm personally interested in. For example, debate conversations, or joining or leaving socially situated non-verbal communication, non-verbal group. So that here each agent has to react to the actions performed by other multiple agents. And these are some scenarios that researchers choose to begin with. And then they also consider basically the following factors. So these the dimensions that you see on the screen are the basically the 6 dimensions that help us to characterize the agent's movement. So as to explain a little bit more on that. So the functional boxes, more like that, demonstrates a goal-oriented behavior. For example, reaching an object, or going from point A to point B with a particular uh, task along the process. Or sometimes there could also be no goal. Could be abstract, like for example, we have no particular goal while dancing, or on the other hand, it could be a goal composed of multiple individual functions. So that's the functional factor. And then during the planning, we basically come up with the sequence of actions that we choose to move from point A to point B. So for example, it could be like avoiding any obstacles while moving in a constrained environment. Then comes the execution, where we decide how do we have a coordinated motion between, let's say, each limbs, between so 2 legs, 2 hands, to realize higher level movement in a physical world or a virtual environment. And the expression is interesting, that we try to display some emotion or mood. For example, it could be like different while walking, while being angry, from walking while enjoying it. And these are the expressions that should be embedded in this motion synthesis experiments. Personal signature is the quality that distinguishes every individual from others. So this could come from a cultural background, or the history of an individual performing a certain action. And the action rendering is the last factor that basically clubs all these patterns together for position of individual limbs and so on, in space and in time. So how does a mocap lab looks like? So it's more or less an open space with multiple cameras mounted at different heights, and there's also a microphone to record audio. And then there are different interfaces. Here I've shown an example of a VCon interface. And basically what it does is it records the different joint positions, rotations. There are also different sensors like accelerometer and so on, to like record acceleration, orientation. We also are aware of like GPS, global positioning system, and so on. And once the experiments have been performed, we basically export the captured data in different formats like C3D or VVH and so on. And this is nothing but like the market positions in 3 dimensions, and like skeleton and motion data superimposed onto each other to be able to like regenerate this experiment in a virtual interface. So and then how is it so what does a mocap performer have to do has to do? So basically once you are in this mocap lab, these mocap labs are generally either marker based or markerless to capture the data. So the image on right is a mocap performer wearing a mocap suit, so this is a marker-based system, and these markers could be acoustic or inertial or magnetic, and there are like many varieties of them. On the other hand, we can also have markerless, which uses two-dimensional video stream, for example, RGB with infrared and so on. So using these technologies, we are able to record the positions of these individual limbs. It's because we, while wearing this suit, we kind of place these markers on the predefined places on the suit, as it is set up in the recording software. And also, you are very welcome to visit our mocap lab at KTH from this link. It is called PMIL. And so before we get into the details of the models, there's a very important thing to consider before working on these models, is to have a very good data representations, because there are multiple ways you can represent your mocap data. But then here I'm just highlighting two examples. One is the Euler angles and other are the quaternions. So imagine we have a plane with z-axis as the yaw, y as pitch, and x as the roll. But then the problem with Euler angles is that so if two of these three axes are lined up are lined up to each other, then basically we lose a degree of freedom, and that's called gimbal lock. So researchers prefer to use quaternions, which is basically shown in red. So just like a high school math refresher, imagine you have a point in two-dimensional space, and suppose we rotate this point in by angle theta. The way we do it is we have a complex number, cos of theta plus sine of theta I, and then we multiply with that the original point to get the new position. So in basically in 3 dimensions, for converting it to a quaternion, we basically use this formulation here, where P is the original point in the space, and the Q is basically encodes the axis and the rotation angle information. And since we are multiplying it twice, then we just we consider half of the angular angle of rotation, and and that's how we compute this product to find a new 3-dimensional position of this rotated point or rotated entity in 3 components, which is the I, J, and K. So quaternion is what, and there are also exponential maps. So these representations researchers prefer while integrating the mocap data in their models. There are many available data sets, but then I try to just list like 4 of them. There is no preference as to why have I included these, but there are really interesting databases available out there for research. So this human 3.6 million is one of the largest data sets that has 3-dimensional human poses and images. Carnegie Mellon University has an exhaustive list of actions and various subjects doing certain certain actions. And then from UC Berkeley, we have this bio-inspired approach to recognize human movements. The last one, congregate data set, is coming from our own lab at KTH. This is basically the data set for freestanding conversational groups and their interactions as to how do they join and leave a freestanding conversational group. And there are many more such available data sets, and despite that, there are still many researchers capturing even more data for their own research objectives. So before I get into the different kind of generative algorithms and how do they work, I just wanted to highlight 2 important things here. So don't get bothered by the details of these models, but just that I wanted to focus that how do we break down the complexity of movements, because there are multiple things happening, right? So one is the physical structure of the human body. And then second is segmenting the time dimensions. And this is like more or less two base approaches of how people try to break down the complexity. So the first example here is, let's say we have different machine learning models doing two different things. So basically, the lower bottom layer is to model like each limb at a frame level, and basically the top layer is to coordinate movements between individual limbs. So in this case, the walking frames generated by the deep belief networks, as I said, like don't. So this is just for understanding purpose. From the top layer for a walking cycle pattern trajectories, we can see from in this side where basically we have a start and an end position denoted in different colors. So this could be a very interesting approach to break down in terms of different models for approximating motion for different parts of the body, and then another model under the top which kind of encapsulates all these individual motions, and then makes one coherent set of motion that the output animation looks like. Um, and so the second factor is the time factor, the temporality. So let's say one example could be, for example, flattening the time dimension to reduce the dimensionality. Obviously, this approach is very old, but then we can also consider temporality as a conditional input, right? And we look into one example each for recurrent neural networks and convolutional neural networks at the end of this presentation. So, so these are the four main categories that I would like to discuss today. So this is kind of old research. So we have I've tried to include research as so until 2017, and so we will be looking at dimensionality reduction techniques, Gaussian processes, hidden Markov models, HMM, and some new approaches from artificial neural networks. So considering the first approach, dimensionality reduction, I found this interesting meme that what happens is it actually lowers the excess dimensions so as to we get a lower representation of the original data, but then it still has to make it still has to be meaningful enough so that we can trace back or decode it back to the original dimension. So that's what happens in this technique. And this is a very good infographic that I found on this website, that basically the transformation of the data from high dimensions to the lower dimensional space is that the lower dimensional representation still retains some meaningful properties of this original data. So just to give you a gist of one of such technique, so probably all of us are aware of this principal component analysis, where we have some high dimensional data. Let's say we have like d+1 dimensional data and we ignore the labels. So we have like d-dimensional data set, and then we compute like mean, covariance, eigenvectors and eigenvalues. So eigenvectors are nothing but the vectors that whose direction remains unchanged when we apply any linear transformation or so. So based on these eigenvectors, we choose like some eigenvectors with the largest eigenvalues, and then we make this M by K matrix here, and then using this matrix we transform the original high dimensional data space data into a lower dimensional subspace like here. So the intuitive meaning of what's happening here is, imagine like you have let's say you have like 1,000 dogs which has some variables. So each data set has correlational variables like height and weight and so on, and length of the dog. So yeah, length and height and weight. So imagine we observe that as soon as the height starts to increase, we also see an equivalent increase in the weights of the dog. So yeah, like for example, if we still want to use one variable without worrying much about its dependency on such large data set, we kind of do this kind of mathematical transformation to just get individual variables without any correlation. And this is an interesting example, motion graph plus plus, where so the image on the right, you see these preprocessed movements mapped using to a low dimensional space using principal component analysis that we saw in the previous slide, and then using GMM. We will look into this later on. Then they are modeled using a Gaussian mixture model. And so basically, if we sample one example from GMM, and we can project it back to the movement space to see that, okay, we are able to we are able to synthesize the original movement using this approach. The next one I would like to talk about is the Gaussian processes. It's basically, as you can see, that more or less you can estimate a function by modeling the correlation of each point with respect to the other points. So the function at this point is basically more correlated to its neighboring points than the points which are further away. And to predict the function at any arbitrary new point based on this correlation, you can use, so you use this training data to predict the correlation of these points to the neighboring points. And basically this is done by taking optimal weighted linear combination of all the training data points. So this is the approach that people use for Gaussian, for building Gaussian processes. And so this is an example using this approach, the Gaussian process latent variable model, where you can see that it's again a non-linear dimensionality reduction technique. But what it does is, let's say this example is coming from Taubert's publication in 2012, where there are so what it does is at O1 we have these handshake movements for a particular category, could be neutral, happy, angry, sad, and so on. And then what we do is we reduce the dimension to the Z space. And then so this is for, let's say, actor 1, and this is the actor 2. Both these actors are performing this handshake. And what we do is we combine these two representation to another I space, which is which actually embeds the interaction between these two actors. And then a hidden Markov model with a hidden variable h is trained on this representation to learn the dynamics, the internal dynamics of these handshake movements. So this is an interesting approach where we use Gaussian processes and HMM. We will look into HMM later on, but with the help of this approach, we are able to now reduce the dimensionality, but it's not linear anymore the way we saw it in PCA. And now it can embed more complex action patterns using Gaussian process. So this is an example of this HMM. It's a parametric hidden Markov model where basically this whole thing is trained on the expectation maximization algorithm. This is usually known as EM algorithm. What it does is it takes the iterative maximum. It uses the iterative maximum likelihood method. So the gist of this model is that imagine we are trying to predict the original model, given that we can't observe the original data points, but in this case we only observe something. We observe the data points that are related to the original model. Hence, hence the word hidden here. So the original model is hidden from us, and we can basically use this hidden Markov model to generate new movements that involves creating a sequence of hidden states, and then generating pose from each hidden state by sampling from its probability distribution. There are different, so the hidden states are, the way hidden states are generated are, there are multiple algorithms that are used for that. One is that we can use some conditional probability. So maximizing the conditional probability of the states given the data, that's called as a Viterbi algorithm. And then during this learning, we actually so that the mean of this distribution, the Gaussian distribution, is conditioned on this certain factor or style of movements that we want to synthesize. So we can basically synthesize a motion based on certain preferred style. So this is more like being categorized on the controlling technique while also learning the dynamics of motion. And then moving on, this is a multi-layer perceptron. So basically an artificial neural net of a humanoid arm picking or like lifting some object. And this is, imagine this is like one hidden layer where the inputs are the initial position and time and final position. The hidden layer could be of any dimension, let's consider 10. And then the output is basically the angular position of the joint at a particular time. So the way it works is in the forward direction, we are training to get the output based on some initialization of this weights and biases of this neural network, and then we backpropagate in the reverse direction to basically nudge the weights and biases towards the output that we are expecting by using different kind of optimization techniques. So basically, I wanted to include Boltzmann machines before we look into this neural network approaches. Sorry. So the Boltzmann machines are, as you can see, it's more or less all the nodes are connected. So each node is connected to all the other nodes, right? And then there's no single output or input, as you can see. But then so we only can see there are these hidden nodes marked in red and the visible nodes marked in blue. And then the model tries to understand the distribution of data using this structure and recreate data based on the learned distribution. So this is an interesting example called the factored conditional RBM, restricted Boltzmann machines. So what it does is it also so first of all, it supports both kind of style units, be discrete or continuous, and then that can represent different factors of human movement. So that's what is happening here, where we are inputting these styles or this condition on our Boltzmann, so RBM structure here. And then what happens is we use like the three-way connection that is allowing the style to control the interactions between the visible and the hidden unit, so that user can control the style of the movement being generated in the output layer. So the output layer kind of outputs the data at time t, and given that input layer has all the information from time 0 till time t minus 1. So I was trying to find an interesting example for motion synthesis, but I couldn't. So I got this reconstruction for handwritten digits using this restricted Boltzmann machine. So you can see that after the training is done, and if we see how the representations have been learned, so it's basically you can see that these are this estimated probability distribution from the ground truth distribution of this handwritten digits. So it's in a way kind of a dimensionality reduction technique, but then the only difference is the way these all neurons in Boltzmann machines are like connected. So each node is connected to all the other nodes. So there was a bit of research on this, especially in I think late 2010, and also this is a very interesting approach for conducting unsupervised learning, research in unsupervised learning. And now moving forward with the more known recurrent neural nets and CNNs, I found one example for each. So what recurrent neural nets are basically, they have this idea of sharing. So they basically share the parameters that learn. So and as they say, sharing is caring. So which is actually a very effective way of leveraging the relationship between one input item and its surrounding neighbors in an intrinsic fashion, because the data is a temporal data. So as I mentioned in the beginning of this presentation, we can either flatten this temporality or use that as a conditional input in our learning model. So the hidden state basically captures the relationship, and which might have some relation to the some inputs surrounding the time t-1 and t+1. And so what it does is it basically learns on top of each other so that these weights basically keep changing in every step. So this is basically a one-dimensional RNN, when there are some higher order RNNs like LSTM, GRU, and bidirectional, and so on, which have done some really interesting, we have seen some good research in these fields. And as we all know, it's part of our machine translation and other models that we use in our phones. So this is an interesting research done from the Max Planck and other collaborators, coming from 2017. So what it does is it's a sequence to sequence architecture, as you can see, and so it uses GRU, as I mentioned. We will not get into what GRU is, but probably we can cover that in the next session. So what it does is, during training, the ground truth here is fed to the encoder, and the error is computed on the decoder. That it also feeds this its own prediction as an input. So the decoder also has like a residual connection, so which effectively forces the RNN to internally model the angular velocities. So let's look into the results, some interesting results from this paper. So we can see that they have covered some four. So I just picked four examples from their paper, where this is output from walking, eating, smoking, and like discussion. So there are like hand movements going on here. So this is an interesting approach from RNN that uses this mocap data. And yeah, and this is a very this is also interesting research from University of Edinburgh and Marza Animation Planet. And this is basically this is the training data, and on which they trained their model. And then you can see the way it has been then they can like synthesize the output motion, and you can see it's looks very natural, and there is no foot sliding or such effects when the synthesized motion has been generated. You can also see that the agent can move sideways if we face it. It can move inside. If we face the agent sideways, it can move. And also there are during this transitional position, we can like modulate the time factor so that it can perform action more naturally. There's also some kind of style transfer going on, where we basically take the content at time level, and they also take you take the style from another model. So there is no relationship between these two motion patterns. However, you can see that the combined model with particular style is able to like create a really interesting animation. You can see that injured or and so on. So this is the original time model, and then once that has been integrated with the style part, creates such animation. And this is I think these are like 200 characters. This simulation has, so it's a really good tool for crowd animation. It runs on GPU in parallel, and then this is a very cool technique. So they use basically autoencoder, convolutional autoencoder to come up with this model. And yeah, this was pretty much my presentation today. And feel free to, so we will be open now for any questions. And also if you have any interesting things to discuss, feel free to reach out to me on these email addresses. Over to you, Nathan.
Yeah, so if anyone has any questions, feel free to speak up as well. I don't see anything at the moment, but maybe I can ask a quick question. So like, let's say if I'm a student and I'm interested in motion synthesis, what do you think is the best place to start learning about implementing these sort of techniques?
Sorry, I couldn't hear the last part, Nathan.
What do you think is the best place to start? Like if I'm trying to get into motion synthesis, would it be to try and implement these different approaches myself, or what do you think is the best way to learn this sort of stuff?
Right. So I think just the way I got started with it, the best approach is to definitely read out the available research out there. But in addition to that, if you are a student yourself, let's say a master's or a bachelor student, you can always find projects that are being done in your university in terms of like small seminar projects or bachelor or master thesis. And because it involves different aspects, as one has to also look into this motion capture technologies and learn those, and then on the other hand model these machine learning models to be able to create some unscripted behavior. And the third aspect, I think it's very important as well, is to evaluate the performance of these models. So I think the best approach is to collaborate and to look out for interesting opportunities in your own university or at your workplace, if that makes sense.
Great, thanks.
So I can maybe say then that how did I learn this? Well, it was very similar by interacting with people who knew it, and we have some of those people at KTH.
Right. So we have more questions. Also, Gustav, thank you so much for being there, especially in the beginning. I was not aware, like there was some technical glitch with my internet. That usually does not happen, but somehow this time it was perfectly timed at the time when we start. So thanks for that.
For those who are not aware, we posted some other links to work that has been done at KTH, at Speech, Music and Hearing, and at Robotics, Perception and Learning. These are not the only things that we've done that involve motion generation. It's not even the only prize-winning things we've done involving motion generation. But if you want to see some of the things that have happened in the very recent years, because Kiran, this presentation was more up until around 2017, right, or so, if I understand correctly, and there's been this field is moving very fast right now, so there's lots of interesting research coming out.
Yeah, great. Thanks everyone for for joining. I think we'll conclude the session here. Thanks, Karen, of course, for the presentation. I'll just stop the recording.